Um, Good morning, everyone. My name is Ademola Adetunji, and I run the MT aspect of geophysics for Meta Earth. So today I'm going to be talking to you about the crustal resistivity structure beneath the Red Lake greenstone belt of the Uchi subprovince in Western Superior Province of Canada. So generally, the overall objective of Meta Earth is to understand factors responsible for differential and mineral endowment within the Superior Province. As you can see, we have a lot of gold here, but we have nothing around here and a little bit around here. And MT is contributing to that objective by delegating the variation in crustal resistivity structure within the Superior Province. Such information can give us idea about the processes that are formed, preserved, and deformed, or formed, deformed, and preserved the crust, thereby helping us determine what are the factors that might have been responsible for mineralization and lack of it. So to that effect, Meta Earth has acquired a total of 925 data from a total of 925 MT stations across the Superior Province along 15 transits. Our latest additions are the Timmins and the Red Lake, and today I'll be talking to you about the Red Lake aspect of this data. So the geologic and tectonic setting of the Red Lake region. So the Red Lake greenstone belt forms part of the Uchi terrane in the Western Superior. And the Uchi is sandwiched between the English River down here and the North Caribou super terrane to the north. The boundary between the Uchi and the North Caribou is not really clear geologically, as it's not exposed to the surface. The Uchi was emplaced at the upper plate setting during the 2.98 GA rifting and magmatism. This was followed by collision of the Winnipeg River terrane with the North Caribou terrane. So the subduction beneath the Uchi was believed to have happened at this time relating to this deformation, and this was accompanied by crustal thickening. The English River terrane sedimentary rocks were deposited at this time, and this was followed by a series of penetrative deformation and the extension, which was imaged by seismic method. And this extension provided some sort of safe haven for the Uchi, where it was juxtaposed on the extensional shear zone. And there was rapid burial of the rocks from this region, and heating and all of other things that happened that time were eventually associated with the gold mineralization in this region. So, and for geophysics, Ferguson et al. In their modeling of the large-scale little probe MT data from the Western Superior Province concluded that this region is typified by a resistive crust with a relatively conductive mantle. They also imaged a large-scale conductivity anomaly, not image. They defined it using the TIPA component of the data. This conductivity anomaly extends for about 600 kilometers, but they could not accurately determine its location. But they associated it with the conductive components of the English River terrane sediments. This model here shows the interpretation of the WS2B seismic line that runs through our study area. This model was combined with refraction seismic, tomography, gravity, MT by these authors to create a geophysical model for this region. And they concluded that the lithospheric architecture shows that this area has undergone subduction, collision, and accretion. At the same time, these reflections were interpreted to be suture zones, fossil of subduction sutures. Also, were the crust beneath the Uchi was interpreted to be at least 8 kilometers thicker than the rest of the region. And in another interpretation based on the processing of the same line, its authors defined a southeast dipping extensional shear zone that allowed the juxtaposition of Uchi onto the North Caribou. And this extension was associated with the slab break-off here and the subsequent gold mineralization. So to the current study, we acquired a total of 45 data at a total of 45 MT stations, sorry. And these are broadband data that runs roughly along the size of the WS2B seismic line. And I extended that with 5 MT sites from the previous little group just to extend this to the northern end of the seismic section and deep into the North Caribou. The stations were like 2.5 kilometers apart, and we used quite a few of them to create 3D control for the 3D inversion. Now, I don't want to bother you with the details of the inversion, so we go straight to the result because of time. Here are 3 depth slices from the top 5 kilometers, from 1 to 5 kilometers, the upper crust essentially. So we have 5 major conductivity anomalies and 2 connected resistivity anomalies at this depth. That's R1 and R2. This is relatively, it's resistive and but a little bit more resistive than the resistivity feature we have in here. The C4 appear to be connected to C4B, and it's along the unconformity relating to the Kochner and the HG Younger anomalies around here. The C3 is just beneath the Boma mine trend, and C2 is along the LP fault. It's called the Little Brook fault for the project. C1 is roughly connected to the Sydney Lake fault, which forms the boundary between the Uchi and the English River terrane. And that's the main thing for the top 5 kilometers. But as we go deeper, we have a transition from the upper part of the North Caribou, which is the Berens River, to the lower part, which is mainly the gneissic rock of the North Caribou, which is more resistive. So we have resistivity greater than 10,000 ohm meters down here. And this is going slow now. Okay, sorry about that. So we have this becoming more like an east-west trending conductivity anomaly, large-scale anomaly for C1 and C3. And the R1 seems to have disappeared at mid-cross, while this part extend pretty much to the lower crust. So looking at the vertical sections taken along these lines at the center of the model, we can see that all the conductivity anomalies are connected to a very large scale anomaly that sits right beneath the Uchi terrane with resistivity of less than 20 ohm meters in most cases. And these anomalies are in turn connected to the possible extensional shear zone here, or deformation, various kinds of deformation zone. With this being greater than 10,000 ohm meters, it actually approaches 20,000 ohm meters in most cases. And this part representing the Berens plutonic complex, and this part representing the North Caribou terrane mostly. Now, this figure here shows the isosurface of this model and it conforms pretty much with every other part of the Superior Province with resistive upper crust and the conductive mid to lower crust. However, we have an isolated, sort of isolated large-scale conductivity anomaly sitting right beneath the Uchi belt here. And we arrange those vertical slices I showed you earlier along their respective coordinates. So eventually, we can see that C1 is connected and is along the Sydney Lake fault zone. This forms the southern boundary of the Uchi belt. And this is the northern boundary of the Uchi belt, between the boundary between the Uchi and the North Caribou terrane, connected by the C2 conductivity anomaly, which in turn is connected to the mine trend at the Red Lake. We also have C2 connected to the LP fault, which is related to the Great Bear gold deposit. And the Uchi is sort of isolated. The boundary between the Uchi is really clear. The boundary between the Uchi and the lower conductivity anomaly is really clear. It's more like it's just sitting on this anomaly. Now, for the interpretation, we combine the interpretation of White et al. And Calvert et al. Here to produce, and that is now superimposed on the empty section from the same line. Bear in mind that the seismic it's 2D in nature, and we have this result from 3D, so there might be a little bit of variation. However, we interpret this line to be the possible suture, the extensional shear zone that connects this part of the cross to the large-scale conductivity anomaly at depth. Also, this is the boundary to the south, which is also connected to this large-scale conductivity anomaly sitting right beneath the Uchi belt. These are other possible fluid path or the load resistivity corridors from which the feature here is transported to the upper crust. And this is interpreted to be a conductive lower crust, like the pond where the gold-bearing mineral was formed. Now, how did that happen? For this interpretation is mainly for the depth slices. So we define these large-scale east-west trending anomaly to represent the northern boundary of the Uchi belt, and it's associated with the gold terrane, the gold trend. Also, this is the southern boundary, and more importantly, putting all the story together from geology, geophysics, and MT, we believe the MT is just depicting the image of all the stories, with the Winnipeg terrane here collided with the North Caribou. So we have the subduction here. There was slab breakoff, which released the heat into the crust via mantle upwelling. The gold, the pyrite, carbon, and sulfur-rich sediments of the English River subducted along with the plate were buried. It was rapid burial, like I mentioned. And this sediment was heated, leading to partial melting. This was followed by devolatilization of the slab, the subducted slab, and also the sediments creating the fluid that created the pond, which the fluid bearing, the gold bearing fluid around here. And all these deformation zones identified acted as the conduit for this fluid to move near the surface. Now, what we measured here with MT is mainly the graphite that precipitated from the carbon, the CO2-rich fluid that transported the fluid, the gold-bearing fluid to the surface. So this interpretation and the scenario is similar to what occurred in the southeastern Australian orogenic gold deposit, as depicted in Hansen et al. 2021. And it also obeys or correlates very well with the global model for the orogenic gold deposits in subduction base. It's a subduction-based model in the convergent margin adjacent to continental blocks. We have the gold-rich sediments, we have the subducted slab, the slab breakoff, the volatilization, fluid ponding, and deformation zones that serve as conduit for these gold deposits. So that's, I hope so overall, in conclusion, there was collision and the barrier of carbon, sulfur, and pyrite-rich English River sediments. There was a slab breakoff, which released the heat by mantle upwelling. We also have post-orogenic collapse, which formed all the low angle detachment faults seen in seismic. There was heating of the sediments, which triggered the partial melting. And also, I must mention that the partial, we have the S-rich granite deposited at the boundary of the English River sediments, which is associated with these K-rich granitic melts. So the devolatilization created the carbon dioxide and sulfur-rich fluid, which was responsible for the ponding and the transportation of the gold from the lower crust to the upper crust. Those were transported through all these boundaries that I've shown earlier, and we finally interpret the conductivity anomaly imaged by MT as a footprint of all these events, and being the interconnected graphite veins. And this graphite originated from the CO2-rich fluid produced by the devolatilization of the ER sediments. So I'm grateful to all these guys for their help with the discussion and the figures and whatnot. Lithoprobe for data, the matter as well, and Compute Canada, especially for the computational resources, and INSAC for the funding. Thank you.
All right, thank you very much, Adi. I forgot to mention, you can either use the chat function or you can stick your hand up, and we have about 10 minutes for discussion. Adi, there's one here from Richard in the chat. Do you think you have localized east-west conductor identified by Ferguson?
Yes, just give me a second. I can't seem to, okay, I have to stop sharing. Okay, yeah, I think that is the conductor sitting along this Sydney Lake fault. And it seems, if we look at the trend, that seems connected to the Sturgeon Lake as well. I was talking to John Ma about that, but we'll discuss for that. But yeah, it is the conductivity anomaly sitting along the Sydney Lake fault, and that is the actual location.
Mark?
Yeah, I don't see myself, so maybe I don't know if you can see me.
Yep, we can see you. You're in a little box.
Not that you need to see me. I'm just going to ask a question. That was great. I'm curious about. We see these big anomalies in modern subduction systems like Costa Rica and Cascadia, and people are now looking at trying to calculate volumes of fluid that might have been generated in that area. Do you think that that's something that you could do? Can you correlate the size of the anomaly to the volume of fluid that might have been generated?
Well, first and foremost, this is an Archean age anomaly, so it's not really fluid. So it's just the carbon, the footprint of the event. So, but back to your question. That's going to be, I don't think that's really possible because whatever you image with MT is just like a recording of the event. And yeah, I in my opinion, it's not possible to do such calculation anyways.
Okay, I might try it. I don't know anything about those anomalies, but I might try it.
Well, you could. I don't know what sort of parameters you would have to, but it's going to involve a lot of numerical simulation to get there, to see what because it's not just fluid, it's fluid mixed with a bunch of other things. So you have to take those into consideration. It might be like, imagine dropping like a stone into a water. You are going to increase the volume. So getting the actual volume, you have to take into consideration that all of that components, which might be a difficult task to.
Be brave.
Well,
Eric has got a question. Could you estimate the resistivity? Could you use the resistivity to estimate the volume of graphite, and from that estimate the volume of fluid flow required?
well, these are mostly, well, to estimate, you need numerical simulation to understand how much graphite would be responsible. Yeah, it's possible via the probably obtaining the actual resistivity value for that area and understand how much graphite would be responsible for such value. Then maybe now relate that to possible fluid. But these are all numerical simulations that has to be done numerically. It cannot be obtained using the MT model only.
Richard's got a comment. You'd have to assume the conductivity of graphite in some way. Connectivity. George, you have a question?
Yeah, so I think the question is in the same line. How much graphite would be needed to make this empty signature? And the second part is there something in the spectral signature that we can say it is graphite, or can it be something else? Because graphite is always the, it's always the usual suspect, but yeah. Do we know it is graphite or not?
Okay, thank you for that question. Actually, I had to, okay, yes. So I had to take some of the slides down because of the time. So in this particular case, yeah, it could be graphite or anything like I have on this slide originally. So it could be any of these. It could be just fluid of any type, and saline fluid mostly, or just partial melt or sulfide. But then one important thing that stands out in this case, it's the connectivity of the graphite. We have a large connectivity because of the fluid ponding. And this is an event that happened over several millions of years. So there was a huge if the connectivity is like great, like very, very well interconnected, then the ability to image it and have higher conductivity is really high. And based on the component of the buried sediments and all other things, we cannot possibly say this is or melt. It's not melt because the way we do it is to try to eliminate each of these possible scenarios by considering all the factors, like I said, that what happened, the history. So, and everything points towards CO2, and I mean, when that's the carbon that precipitated from that CO2 that gave us this graphite in this particular case. I hope I answered your question.
Yes, thank you.
Okay, I think we need to move on. Thanks very much, Ademola. And if anybody has questions, you can just contact Adi directly.
Thank you.